It's the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode number 52, where today we are going to be talking about thermodynamics. We're going to be talking about entropy and the disorder in the universe. So if you guys have heard of the term entropy before, you might know what we're gonna dive into today. So it's gonna be exciting.
And if we would have been releasing one episode per week since the beginning, this would be our 1 year anniversary. So that's cool.
Oh, is it? No way.
I mean, 52.
Oh yeah.
But,
that way. Yeah. Well, obviously, I forgot about. Okay, I didn't understand that.
I mean, at one point we were releasing episodes like twice a week in the beginning. But that was during the summer.
June,
so
I can never forget. I think it was June or July. We released like 1 or 2 episodes because we were just really lazy. Huge drop in downloads, and obviously, like, we didn't get that many episodes out. So like it was kind of inconsistent when we were just starting up the podcast. But I think now we're very comfortable with our weekly schedule. So yeah,
That's
here we
right.
are.
All right. Getting into this episode. We want to thank you for 6,000 Spotify followers today. And on YouTube, 350 subscribers. Thank you very much.
Always nice. Always nice.
If you are watching this episode or listening to this on Spotify, you can check it out on YouTube, where we record this and where you'll be able to see my new haircut.
Hey,
okay.
That's true. That's true. This is a long time coming. You've had the man bun type hair for quite a long time. So here we have it.
I mean, not quite man bun.
No, but like enough to make one. Like you had a lot of hair, is what I'm saying.
It wasn't. I mean, anyways. The point is that you should come on YouTube and like the video and subscribe. Maybe
a lot of Spotify followers and like listeners actually commented on YouTube saying, "Hey, we're from Spotify, and we really enjoy your content." So like it's always nice to hear. So talking about nice things to hear. Let's talk about the comment of the week, shall we?
Comment of the week.
So the comment of the week was from Brandon Miles. It was on the most recent episodes on the YouTube comment section, where he said, and I quote, "This episode was awesome. Touched on so many subjects. Such an underrated podcast. You guys are going to blow up in the coming years for sure."
Hey.
He is sure that we will blow up. Thank you, Brandon, for your comment, for your support. I know Brandon has been a long-time listener. I think a lot of these comments of the weeks, like these really nice, like we start to notice that all of them or a lot of them have been listening to our podcast for quite a long time.
Yeah, and so we do remember, like, if you commented on an episode like way back, like episode 2 or whatever. Not that anyone actually commented, I don't think, but like we actually remember the people who like subscribed early on and commented very early on. So yeah, I still remember.
I mean, we still had like 20, 30, 40 subscribers. Like we were just growing slowly. Yeah. And people were still listening. Like I mean, that was good. So yeah. All right. Well,
anything else, or should we?
I don't think so. I mean, I think any downloads news? I don't think so. Like we passed 75,000, which I don't know if we mentioned before. I think that was the same for last week. Which I think is nice. Did we mention it before?
I think we said 75 last week.
We probably did. Okay, I'm not too sure, but anyways, it's another 25 to the big 100. So
that's gonna be nice.
That's gonna be very exciting. That's gonna be very exciting. So yeah.
So
I think that's it. Yeah.
Let's start with
Let's get into it.
This episode is going to be mostly about the second law of thermodynamics.
Okay, because it's this. Okay, a little description here, because so we are actually taking Parker and I are taking a thermodynamics course where we're learning a lot of these different ideas, and our goal of this episode is to take all the ideas from there, all the ideas that we have in our head, mash them together, and produce a perfect episode. So in our
not
class,
necessarily.
as I was saying, well, I don't know, but as I was saying, like in our class, we focus a lot on entropy. And the reason we do that is obviously very well established, because we need to, right? And we're going to get into why the second law is so important. So the reason we're going to get into the second law today is mainly because the second law is one of the most important laws. So that's also another reason why we're going to be focusing on it today.
That's absolutely right. And so we'll start with, we'll just present the first, or the zeroth law and the first law, just to then move on to the second for the rest of the podcast. So the zeroth law just states that, okay, you have system A, system B that are in thermodynamic equilibrium. That just means that if system C is in thermodynamic equilibrium with system B, then system A is also in thermodynamic equilibrium, whatever, with system C.
Yeah, so basically the idea is so thermodynamic equilibrium. So equilibrium, I think it's it's a very it's a very intuitive word. Like it is telling that something is equal. And when we say thermodynamic, anytime thermo, anything with T usually comes up, it's usually temperature, right? Yeah. So when we're talking about thermodynamic equilibrium, we're talking about two systems being at the same temperature.
But there's also mechanical equilibrium, which is the same pressure. And there's also chemical equilibrium, which is like the same dilution.
Isn't it like number of? No, wait, is that?
I think it's the same dilution of like a solvent.
Solvent.
Like if you like, for example, if you have like particles of like tea at the bottom of your cup, and then you have like water on top, and then when you like mix it together, then that becomes a chemical equilibrium.
You're right. It's with the concentrations of the particles.
Yeah, that's what I
was
was looking
the word
for.
we were looking for. Yeah,
concentration.
So those are the three types, and well, in thermodynamics, you can assume that thermal is the most common type because we're talking about temperature changes. Because
I mean, actually, it's not the most common.
Well, okay,
I think they're all pretty equal.
It's the most common, but no, the reason I'm saying is because temperature change is directly related to energy change, right? Because when you say this system has more temperature, what that basically means is all the individual particles.
Not necessarily. Temperature change does not imply energy change, because that actually brings us to the first law of thermodynamics. That states that the change in energy of a system is equal to the heat put into the system plus the work put.
I guess there are other factors, but the point I'm trying to get at is like when we say like temperature is or like an increase in temperature from like one state to another, like what I'm trying to say is like the particles in the system are gaining more energy, or at least assuming like some things stay constant, right?
Yeah, so assuming like you fix the number of particles and also the volume and all that stuff, then if you increase the temperature, then the energy of the system will increase. But if you supply heat to your system while letting the system do work onto the environment, the first law of thermodynamics states that the change in energy of the system, well, as long as the heat and the work are equal and opposite, then the change in energy will be zero.
Yeah. So again, there are other factors that do play into effect. But anyways, like again, the purpose of all this stuff is because when systems are in equilibrium with each other, there are very interesting properties that get satisfied, and there are very interesting things that happen that we're going to be getting into as we move further into this. But another interesting thing that I actually just thought about was kind of a random thought, but it is very directly related to this. Let's say it's like 5 degrees outside, or 0 degrees Celsius, by the way, not for the Americans out there. That's really cold. So let's say it's 0 degrees, 5 degrees outside. Basically, it's cold, and you put a metal spoon outside, and you put a wooden block outside, right? Now, after, let's say, 20 minutes, you touch the metal spoon, and you touch the metal block. And you touch the wooden block. Now, which one's going to feel colder? Like the metal spoon, right? Obviously. Yeah. but the temperature of the metal spoon and the wooden block are the same. And that is where people are like, wait, hold up. So if they have the same temperature, how can one be colder than the other? And this is an interesting fact about the properties of the system. So in this
Like
case,
thermal
the metal
conductivity.
spoon. Sorry?
You're talking about thermal conductivity?
Thermal conductivity, yeah. So the spoon is metal while the wood is porous. Well, the wood is wood, but like the wood is porous, a porous material. What that means is there are like these small gaps, microscopic gaps. Obviously, you probably can't see it, but there are these microscopic gaps that when you put your finger on the block of wood, all the temperature from the wood does not directly go into your finger. Because when you put your finger on that piece of wood, there's a lot of air that you're also touching, right? Like there's a lot of just gaps, empty gaps, because as I said, the wood is porous. Right? So there's a lot of empty gaps that you're also putting your finger on. So the wood is not able to directly give you all of the energy.
Well, actually, it would be your finger losing energy.
Well, yeah, technically, because it flows from heat. Yeah, sorry. That's actually more scientifically correct. I was just trying to provide a picture like how it's flowing. But yeah, technically your finger, because it's hotter, it's the one that's releasing the energy to the wood. And again, because of the porous material of the wood, it's not going to all parts of the wood. Now, contrast that with the metal. The metal, on the other hand, is very, very rigid. And there's almost no air gaps or air holes in that material. So the moment you put your finger on that, every part of your finger is touching at least some part of metal. So all parts of your finger are giving away heat simultaneously, and you have the feeling that it is colder, even though in actuality they are the same temperature. And I think that's a pretty cool thermodynamic fact. It's a really weird light hitting my face right now. I don't know if you can notice.
I think right now is a good time to introduce the concept of entropy, because I think one thing that entropy is very useful for. One thing is that it's hard to really grasp what entropy really is, but it's used to define things like temperature and also pressure and chemical potential and and all these things that if I were to ask you as a non-scientific question, like how do you quantize or quantify temperature? It has to do with feeling, right? You like today you feel that it's hot out, and the next day you feel that it's cold out. But how do you assign a number to it?
Yeah, that's the answer.
And
that's the question.
We've done it with like mercury and also bending metals, right? Like you have one metal that doesn't expand as much as another metal, and then so when you supply heat, it'll bend one way. And then you can put like a number scale on it, and it'll tell you the temperature.
That's an interesting way to do it. Actually, I never thought of it. That's pretty cool.
Yeah, it's actually how they do like dial thermometers. Like how there's a thermometer and there's like a dial that turns.
Okay.
And it'll point to the temperature. It's actually the arrow or whatever is attached to a coil of metals, of like. These two metals, one side is a metal that doesn't expand as much as another metal under like a temperature increase. And so when the temperature increases, the metal that expands more will push the other metal to bend one way. And so that's what happens. The coil lengthens and it moves the
That's pretty interesting.
I actually learned that from Walter Levin, the guy who posts the MIT physics prof.
Oh, yeah. I've heard of it.
He had a lecture. He had a lecture on temperature.
Really? That's so cool. That's actually a pretty cool fact.
That's very cool.
The temperature dial. That's pretty interesting.
Yeah.
The thermometer
and so,
dial.
Entropy. Talking about entropy. So, okay, here is the equation for entropy.
Do we get into the equation?
Yeah, we have to get into the equation.
My God.
So, entropy is denoted by an S. Okay, and its S is equal to the Boltzmann constant times the natural log of the multiplicity. of your macro state. Now we will
Like we had to get into this. Right?
No, we have to. We definitely
okay.
have to.
I mean, we kind of did, but like
we definitely have to, because in order to really understand what entropy is, you have to know how it's calculated. And so the Boltzmann constant is just a constant. So we can kind of ignore that. It's just a fixed number, okay?
Because remember, like when we're talking about like entropy, especially in this regard, like where we haven't even defined it yet. Like we're just talking about this word called entropy. So right now we're trying to understand its relationship with other variables. So KB, or the Boltzmann constant, right? It's denoted by a K subscript B. So that's simply a number. It's simply a number that is only for it's only to equate the entropy and this natural logarithm of the multiplicity. But if we're just looking at how these variables change, we can just ignore the Boltzmann constant, right?
So we're looking at a quantity that is defined by the natural logarithm of another quantity. And you heard me say it was the multiplicity of a macro state. So we'll break that down really quickly, or maybe not so quickly, but so that you'll really have an idea for what it is. So a macro state is like a general state of affairs, okay? For example, if you have 5 coins in front of you, the macro state will just be how many heads you have and how many tails you have. So you can have, so one microstate might be just all heads. One microstate, macro state might be 3 heads, 2 tails, right? It's just a vague description of your system versus
the
micro state.
Oh, yeah. So the micro state is where it gets a little more, not complicated, but a little more, in detail with the system. So continuing this example of the coins, if let's say we're talking again, I think you said we have 5 coins, right? So let's say we have 5 coins and the macro state is 3 heads. So we're automatically told, well, if we have 3 heads, we obviously have 2 tails. Now, we have 3 heads and we have 2 tails and we have 5 coins. Now, each coin can individually be a head or a tail. So that would be the micro state of each coin. So the micro state is more relating to the individual quantities of the system, while the macro state is talking about the general idea of the system.
I think the way you put it is a little bit misleading.
Okay, maybe
because the micro state doesn't depend, like there's no micro state of each coin, right? It's the micro state of the system itself. So for example, under the macro state of, let's say, 1 heads and 4 tails, you can either have heads, tails, 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 or tails, heads, tails, 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 heads, whatever. The micro state is basically where the heads is, because you can have, I think it's like 6 different, in this case, it's like 6 different micro states that have the same macro state.
No. And so it's n plus 1 macro states, but it's 2 to the n micro states, right?
No, but I'm talking about for the 1 macro state.
Yeah.
That is 1
heads, for the 1 macro state.
And 4 tails. Mm-hmm. There are 4 possible micro states that
because there are 4 possible positions that it can be in, right? So this kind of brings up the idea. So if any of you are interested in statistics, this actually brings up the idea of a combination versus a permutation, right? So a combination is so let's say we have, again, you want to give the coin example? Let me try to give an easier example. Let's say we have the letters A, B, C, and D. Very simple. And we're trying to get 2 letters out of that, right? A, B, C, and D, we're trying to get 2 letters. So we can get A, B, we can get C, D, and then we can get some combination of those. So let me explain the difference between combination and permutation, and then we can understand, I think, micro and macro states a lot better. So, for example, as I said, A, B, C, D, and we're picking 2 letters. Now, A, B, and B, A, what's the difference between A, B, and B, A? The only difference is the order. So if, let's say, we're picking 2 letters and we pick A, B, well, if we're just talking about the letters that we picked, A, B, and B, A are the same thing. Like, they don't mean anything else. So that is a combination of the 4 letters available. However, if we are talking about the order, oh, that was a little too loud, the order of the system. So for example, AB is different from BA. That means, let's say they represent individual quantities that, are like, for example, let's say it's which coin I take out first, or which letter I take out first. So if we're talking about the first letter, then AB and BA are very different, because AB I'm picking A first, BA I'm picking B first. So that is a permutation, right? So a permutation is basically where order matters. A combination is where order doesn't matter. So in multiplicities and these micro and macro states, or in the micro states at least, order matters. Because if we have a tail in the first, again, going back to the coin example, if we have 1 tail and 4 heads, right? The micro state of 1 tail and 4 heads is different from 1 head, 1 tail, and 3 heads, right? The micro state is different, but the macro state is the same.
Yeah.
Does that make sense? Because a micro state is a permutation, right? Where it depends on where that tail is. Because the micro state would change.
But let me know, because you're the stats guy here.
Yeah.
So from what I understand, in the coin example, we're not talking about permutations per se, because it doesn't matter. Like if you label the coins 1, 2, 3, 4, 5, and your micro state is like the second coin is flipped to heads.
Okay.
Right? We don't care which coin is in that second position, right? Like it doesn't matter if coin 3 is flipped at heads in position 2. It just matters that you have the general outline of the tails, heads, tails, tails, tails. So that would just be a combination, because you don't care about the order of how the coins were picked out. It just matters that it's tails, heads, tails, tails.
But
tails.
am I wrong when I say that a micro state of tail, head, head, head versus head, tail, head, head, head? Like, wouldn't that be different? Wouldn't those be 2 different micro states?
Yeah.
Yeah. So exactly.
Okay. So you're right.
That's the entire point that I'm trying to bring up, right?
Yeah. So you're
right.
You're right.
If A, B, and BA are 2 different things, that means it's a permutation that we're dealing with.
For sure.
Right.
Now, I'm sure that some of the listeners out there are very confused why we're talking about coins right now, but it will become very evident. Okay, so now we have to talk about multiplicity. Okay, multiplicity is just the amount of microstates that are in a macro state. For example, the easiest example is all heads. All 5 coins are heads. The multiplicity is 1, because there's only one way that you can have all heads, and if they're all heads, right? But the multiplicity suddenly increases if your macro state becomes 1 heads, 4 tails, because suddenly you can have, one micro state, as I said before, will be like heads in the first position, or heads in the second, third, fourth, fifth, and each one of those adds to the multiplicity. So let's say there are 4 or 5 ways to do 1 heads, then the multiplicity of that macro state is 5. And now by symmetry, the macro state with 1 tails is also going to have the same amount of multiplicity as 1 heads. And if you do them, you don't really have to do the math, but you can kind of imagine, as let's say the amount of coins you have increases to like 100 coins, and then you say, what's the multiplicity of the macro state with 50 heads, 50 tails? It's going to be vastly greater than the multiplicity of the macro state that has only heads, right? Because you can literally pick out any order. As long as there's 50 and 50, you can pick out any order of heads and tails. And the reason why this is important now, because it connects directly to the equation for entropy.
And before we get directly into that, I do want to clarify something. So the permutations that I was talking about were for the microstates and the microstates itself. So now that you bring up the idea of macrostates and their relationship with microstates, now macrostates are actually not permutations, they are combinations, right? Because like as we were saying, like if we have 1 head in the first position, or 1 head in the third position, or 1 head in the second position, it's still 1 head. So the macro state is the same no matter what. That means the macro state does not depend on the order of the elements. So when we're calculating this multiplicity, what we usually like to use, again, instead of permutations, is a combination. And again, for anyone like studying university level math, like if you've ever, or like even high school math, like if you guys have looked at combinatorics before, then you might kind of understand like the stream, or at least like the argument that we're trying to pan out here with combinations. So yeah, let's get into the entropy equation now.
Yeah, right. So entropy, the second law states that entropy tends to increase always.
That's it. That's the second law.
There might be like some misleading events where locally the entropy decreases, but as soon as you zoom out, you'll see that the entropy actually increases.
First up. I just noticed we still haven't defined what entropy is. Like, well, like, okay, I mean, we're talking about it in terms of micro and macro states, but like no one really wants to hear that. Like, first of all, what is entropy?
I think now that we've presented like the coin argument,
okay,
it will be very satisfying to now say that entropy is somewhat, hand-wavily a measure of disorder.
That's the term I was looking for. Yeah.
So if you can imagine, like the natural log of 1 is 0. Okay, so the entropy of this coin system that has the macro state of just all heads, that has a multiplicity of 1. So, you plug that into the entropy equation and you get an entropy of 0. Now, as soon as you start flipping coins into different macro states, you'll have higher and higher multiplicities, and it will be, you will have higher and higher entropy for those specific macro states. Now, if I were to tell you, you start off with your coins all on the heads, all on the heads flipped up, right? And then you just, you put those coins outside, for example. You just leave them outside, and then you check 10 years later, okay? What are the odds that you come back and you find all of those coins still heads facing up on the street, right? Exactly where you left them. Very low. Very, very low. Because, the wind can blow. Someone can, flip the coins as they wish. The rain could, I don't know. Anything could happen. Literally anything. And so this is kind of an example where it's so much more probable that over time you will find your coins in a different macro state with automatically higher entropy. That I think another really good example is if you have like a stack of papers on your desk, like what are the odds? Let's say you leave like a window open, or not even, right? You leave that stack of paper perfectly ordered and squared off on your desk.
Okay.
And then, anything can happen that can, blow the paper, blow the papers all over the room.
Okay.
I'll say, a tornado, whatever. Anything can happen. But it's so easy to go from that perfect orderly state to a disordered state. But you'll never see a tornado swirl up those papers back into a perfect stack. Because that would be decreasing the entropy.
That is true.
Of that paper system.
Let me give you an easier example. Much easier.
I thought that was pretty easy.
I mean, okay, that's okay. I mean, I don't know, the tornado came into it and everything, but if we're just think about a deck of cards. Think about a deck of 52
This
cards.
is the exact same argument, by the way.
Yes, it is. It's the exact same argument. It's just an easier analogy to understand. Okay. So think about 52 cards. We have a deck of playing cards. It's a brand new stack. So what do we know about this stack? We know where every single card is, right? We know where the king is, we know the queen is, because it's all ordered in the exact same way. When you open a brand new deck of cards, it's always ordered in the exact same way, and that's how you're going to get it every time. So this is the system where it has the least amount of entropy, where everything can basically be predicted, where you know where everything is. Now, as we shuffle the deck, let's say we shuffle it just once, we have already increased the entropy. Why? If we're talking about just the disorder argument, then we can look at it with, well, the cards are more disordered. But scientifically, like mathematically, what's happening is we are less likely to predict where every card is. Now, as we continue to shuffle and shuffle and shuffle, and we keep shuffling, when do we achieve this maximum entropy? Because that's also something that we should maybe touch on. Because every system has a maximum entropy that it can achieve. And in this set and this deck of cards, the maximum entropy will be achieved when each card has an equally likely outcome of being pulled. So let's say I put all the deck, all the cards face down after shuffling them like 100 million times, and I put them all face down. If the probability of me picking a king of hearts is the same as the probability of me picking a two of hearts or a two of spades, or any card, any two cards have the same probability, that is maximum entropy. That means it has been disordered to the maximum possible amount. It can't be disordered anymore, right? Because when you already have them at equal probability, how can you can't disorder it in any more way. So I think the deck of cards is the standard example that everyone gives when you're asking, can you like explain entropy to me? And also because I think it's an easy analogy.
And now I also think that the listeners are thinking to themselves, why are these physics students talking about decks of cards and
not
coins?
very much related directly.
Once again, how is this related to physics at all?
Mm-hmm.
Okay, because this is why. So you can actually calculate the multiplicities of macro states and all that stuff for gases and like actual systems of everyday life. Now, because thermodynamics, also referred to statistical mechanics, deals with very, very large numbers, and when we talk about, let's say, a cubic meter of air, you can't actually say anything about an individual particle of air and actually say, okay, this particle is moving at this speed, this particle is moving at, you can't. You have to really generalize and say, on average, the average velocity that we can find any one of these particles in is X or whatever. And this is based on like the temperature, the pressure, and all that stuff. There are complicated formulas. If I were to just say it to you out loud right now, it wouldn't make any sense. But if you actually go through the mathematics of it all, there are actually surprisingly quite concise equations that you can just plug in values that you know about the system, like temperature, like volume, like pressure, and all these things that you can actually calculate on a macro scale. For example, if I have a box, once again, of air, I can easily calculate the pressure. Oftentimes it's just going to be 1 atmospheric pressure. Is that what it's called?
Yeah, one atmosphere technically.
One atmosphere.
One atmosphere.
And volume, obviously, it's a box. You can just do side length cubed, whatever. You can just calculate these easy values to calculate. Also temperature.
And these are the macro states. These are all the macro states.
And this will be a macro state. You plug that into the formula, and it will actually give you the entropy, because once again, the entropy is directly related to the multiplicity. And so if you play around with like the multiplicity of a system, you plug that into the equation for the entropy, you simplify it as much as you can, and you will have like relatively an easy time calculating these entropies of systems. And what does that tell you about the real world? Well, we're interested in thermodynamics. So how systems interact thermally with other systems. And so what happens, naturally, how do you describe heat flow using entropy? Well, first of all, you start with the second law that says that the entropy of a system tends to increase. And so let's say we have system A. It has a uniform temperature. it is at maximum entropy already on its own. And we have a system B, which has a higher temperature than system A, and it's in thermal equilibrium with all of its constituents. And then we put them into thermal contact, meaning that they can exchange energy. So why is it, intuitively, obviously, you're saying, okay, well, the heat will go from B to A until they're at the same temperature, and then heat will just, stay constant. But if you take a moment to sit back and to actually think about it, like, why is it? Why can't the cold system make the hot system even hotter and the cold system even colder, so that like why does heat have to flow one way? Do you have an answer for that, Ray?
I am stumped. I'm not sure I have an answer to that at the back of my head, but I think there is an answer to that for sure. Like, why?
Is there? I don't know if there's an answer to that. I think it's like it works out nicely. I think you can make the argument that if it didn't work that way, then the universe would not really function so well. But there is no it's kind of asking how the creator of the laws of physics was thinking, when he was making them. You don't really know.
So I think we actually do know this because we've seen this equation, the Fourier heat conduction law. And that law basically loosely states that that heat travels to the largest, or heat travels from the largest temperature to the lowest.
But there's a difference between somebody making an observation, right, and saying, okay, heat flows from hot to cold. But also, there's a difference between saying that and explaining why that is. Like, why does it automatically say, hot goes to cold? Mathematically, it works out due to the second law of thermodynamics, because it just so happens that if you have a cold system and a hot system, you can actually explain spontaneous heat flow from the cold to the hot, causing the, locally, I guess I should explain first that the more energy you have, the more entropy you have, or I guess it's related to temperature. The hotter you are, the more entropy you have. Mm-hmm. And essentially, if you were to exchange heat between these two systems, the entropy of the hot system would actually decrease, while the entropy of the cold system would increase. The issue, or I guess there's not really an issue here, but it's kind of misleading, because you might think, oh, I thought you said the entropy only increases. Well, actually it does, because we're zooming out. We're looking at both systems together in one, as a single system. And so the entropy of the hot system is going to decrease less than the entropy of the cold system is increasing. And so in total, you're going to get a net increase in entropy. And this can all be done mathematically if you want. And
this is also kind of like a fundamental law that if even so the second law not only kind of states that the entropy always increases, but it also states that if two systems are kept in thermodynamic equilibrium, or not equilibrium, in thermal contact with each other, as you were saying, system A and system B, let's say we bring them into thermal contact, the individual entropies will be less than or equal to the total entropy of the new system. And that is also a very interesting fact, right? Because the individual, so let's say, I think you brought up the idea that B was hotter than A, I believe. So in that case, right, B, the entropy of B, because the heat is going out of B and into A would be increasing and B would be decreasing, right? But A would increase more than B decreases. So the net entropy would be...
That's actually what I just said.
Oh, okay then. Sorry, no, because actually I was actually reading just like questions. I would just answer just asked why do things flow from hot to cold, and I got all these I got this really funny answer. I really want to read out. And this one guy on Quora just answered, let's say there's a rich person with a lot of money and there's a poor lad with no money. Unfortunately, money is made by man and not for nature. If it was made by nature, they would have created an equilibrium and there would have been no rich, no poor. I just love that line. Sorry. So anyways, I mean, that's a way to think about it. But anyways, I mean, why it flows from hot to cold is, I guess, a scientific fact that we're just dealing with. But if you guys, the audience, the listeners, want to learn more about these scientific facts, that was a very smooth transition there, you guys can check out brilliant.org. Clapping sound. So we are proud to say that Brilliant is the official sponsor of the Math and Physics podcast. And they have a lot of topics where they talk about exactly what we're talking about, right? Thermodynamics, for example. They have a really cool science essentials course that Parker and I were looking at, where they talk about heat, they talk about heat flow, they talk a little bit about thermodynamics here and there. They have a physics of everyday course where they talk about how refrigerators work. I think we found that really cool, by the way.
And it's actually what we're learning right now as we speak in our thermodynamics course.
So, exactly. So you have the opportunity to learn university level courses at your home, for free. Well, it's not for free. I mean, it's a premium membership, but the idea is that you are able to learn all of these interesting topics. They have a really cool daily challenge section that Parker and I were trying out, and it's just based on logic. It's really cool, some really cool questions and answers that you can learn. So, I mean, in all, like, they have some really cool programs that you guys should check out. And
it might not be free, but if you do love sales, let me tell you something. You can actually go to brilliant.org/MPP to get 20% off. The first 200 of you will get 20% off your premium membership. Yeah. So make sure to click the link in the description and to start learning, to start expanding your horizons.
Mm-hmm. And I mean, again, you don't only have to be like a science student to really like this. Like, this is really with anything. I think they have topics, ranging from, again, because Parker and I are mainly focused on the science, we've mainly focused on those. But again, like, they have topics ranging from all sorts of niches. So you guys can go check it out. At least, give it a quick look.
For sure.
Yeah. So what I do want to talk about, and I think it was a good transition so we can change this into the entropy of the Big Bang, right? So we're talking about how the entropy of systems change. But what about the entropy of the universe, right? So obviously, taking the second law as it is, the fact that entropy is increasing, we can say that the entropy of the net universe, of everything in the universe, is essentially increasing at all times. Now, that means that it would have had to start from some very small number, right? Because if it's increasing, it probably started, because it can't start at negative infinity, or it can't start at, so it has to start at something, is what I'm trying to say. So at the moments of the Big Bang, or right after the Big Bang, right, there was no matter that was created. It was only light. It was not even dust. It was just energy, right? So there was nothing that was really there.
It wasn't light.
Light, I mean, like energy. Okay, light is the wrong word, actually. Light is the wrong word. Not like visual light, but like energy was, something was expanding, is what I'm trying to say, right?
Yeah.
So the moment the Big Bang occurred, I think that's when the entropy clock started. And that is when we started to see that the entropy initially increased. So the question that a lot of people have is, well, was the entropy zero? Or was it a constant fixed value when the universe was in the singularity phase? So, like, a lot of people assume in this Big Bang model, the universe was in this singular phase before expanding into the universe we know today. And we call that the initial singularity, right? So the question is, when the universe was just this infinitesimal point in space. Well, space wasn't even created yet. But when the universe was that, Like, what's the idea of entropy over there? Like, how do we even talk about disorder or order when the universe is just a bunch of energy?
I don't really think that any physical concept was defined at the singularity. Like, you can't talk about
Maybe not.
projectile
Okay, but what about the
motion.
moments right after? Okay, maybe not at the singularity, but moments right after, right? Like the universe just started expanding. What's the situation with entropy? What's the situation
it's
with entropy?
increasing. I think that's
I mean,
all we
yeah,
could say.
it's increasing, but the idea is that it started from some terminal number,
I mean,
and
if you
the
want,
idea is sorry.
if you want, you can kind of define entropy at t equals 0 to be 0.
Yeah, so that's the entire point. So if we're defining it as 0, and we know it's net increasing, that means we have had entropy equals 0 in the universe.
I don't think it's. I think it's more like if you were to have, like, let's say your graph. You know how if you have like a quotient of like this is back in like grade 12, where you would have like a quotient, and then you need to solve for like the hole in your graph, and so the graph looks linear, but at a point you have a hole because the denominator goes to 0, but it, you know, do you know what I mean?
Yeah, I know what you mean. I know what you mean.
So let's pretend that this like undefined point is at t equals 0 for the universe, time equals 0. I think like the actual point, like the limit, if you were to look back, as the limit as t goes to 0 from the positive side, the entropy tends to 0. But at the actual value, it's just undefined. You can't say anything about entropy at the singularity because it just doesn't mean anything.
I guess.
You also can't talk about like what is the temperature of the singularity because you don't even have space. You don't even have space. How do you calculate pressure? How do you can't really talk about anything.
They're just thoughts, right? Like they're just like Big Bang thoughts. Like it just that I've always wondered because like entropy and the universe play a very close relationship, right? Because and I think we can start this pretty cool idea where the heat death could be caused because of entropy, right? Because entropy, again, as we were talking about the maximal disorder, when does that happen? When it's equal probability for all events. So in this case, in the case of thermodynamic equilibrium, when we're talking about the whole universe, the maximum entropy, the absolute maximum possible entropy of the universe will occur when everything is at the same temperature. So the whole universe is in thermodynamic equilibrium. And when
I think that can only happen when there are no more stars nor black holes, because black holes do evaporate very slowly, and eventually, like, stars will die before like the black holes evaporate, and so the universe will get to a point where there are just no more stars. It is just a black universe, and you will see. Well, you won't see anything, but there will be black holes just peppered all over the place. And some black holes will become super massive black holes as they start to attract each other very slowly, just like how gas clouds can attract each other very slowly to become a star. I think the black holes will actually, now that I think of it, I guess it will happen like relatively locally, but because the universe is expanding, some black, just like for us, we'll never see, like some stars we'll just never see because they are moving away from us faster than the speed of light. And so that will be the case for some black holes. They'll just spread out everywhere, and as they all finish to evaporate, it will just be kind of this isotropic black soup of matter that is just all the same temperature. And at that point, a very long time from today, there will just
very
be
long.
a heat death. The entire universe will just be the same, literally the same, everywhere you look, everywhere you go.
That would be very insane. Also, just a quick, very insane. Oh, quick clarification: the galaxies don't move away faster than the speed of light.
Yeah,
it's
it's
space
just
that's
the
technically
space, yeah.
space that's being created faster than the speed of light, so it gives us the illusion that the galaxies are moving away. But yeah, I mean that's an interesting point. Like that will be, I mean that is a potential future for our universe, right? Like when all of these black holes, when all of these stars basically dissipate into, like, the absolute end would be probably when all these guys are just protons and neutrons and just like bunches of just matter floating around, all in equilibrium.
Well, I think there will still be like elements floating around, because how do you really decompose the elements into protons and neutrons?
Let me bring up a quick thing that I'm reading. Maybe I can put it in the description. Just we should remember a quick thing that I'm reading. I just want to quote something out of here, like in case I don't get anything crazy wrong. But this one article that I'm reading is in the far distant future, stars would have used up all their nuclear fuel, ending up as stellar remnants such as white dwarfs or black holes. They will eventually evaporate into protons, electrons, photons, and neutrinos, ultimately reaching thermal equilibrium with the rest of the universe. And then they continue on to say that this process of cooling down can take, can take 1 followed by 100 septillion. That's 10 to the 26 zeros. So that's how long it would take. Years. Those are how many years it would take. And then the temperature would drop to almost like near 0 Kelvin, near absolute zero. So, I mean...
Wait, the temperature would drop to 0? Is that because the universe is expanding? So
yeah, so it's weird because it's called heat death.
Yeah.
But it's not really heat. You know, it's lack of heat.
So wait,
because it's expanded to
eventually...
such a large space that there's like not enough heat for the whole universe to continue. Like stars would not be able to form if all the matter is just so.
How is that possible? Because then that would be entropy 0. If everything just stops moving.
Hold up. Wait.
Houston, we have a problem.
Wait. What?
I mean, I don't know. I don't
Okay,
think
again. No.
Temperature goes to 0.
No. Well, this is an interesting...
I don't think temperature goes to 0.
Well, it could take as long as so many years, with the temperature dropping to around 10 to the negative 30 Kelvin. That's what they say.
That's not 0.
I mean, it's not 0,
That's
obviously.
not 0.
Well, it's not going to achieve 0. I never said 0.
Because entropy 0 is only defined at like 0 Kelvin, right?
Yeah, so 0 Kelvin will just not happen. That would just not, no.
But even if there's a really, really low temperature, if it's spread out over the entire universe, then we will still have like an insane amount of
volume,
entropy.
right?
Yeah.
Right, because it's about how big the damn thing is too, right? Like because we have this huge universe. Sorry. We have this huge universe with, even though it's such low temperature, the entropy I do not believe will go to 0. That would just not happen, because it will have to increase. It would just keep increasing again. But the thing is, it would increase until it reaches that maximum entropy, right? Because we were talking about earlier how all systems have a maximum entropy where
I think
you can't put any more work. Unless you do work on the system, which is different, internally speaking, there will be maximum entropy at some point. So if we're talking about the whole universe, remember, the whole universe, we can't really put in energy from outside, because any energy we put in to the universe is technically internal, because we're in the universe. So when the universe ultimately reaches this maximum entropy regime, right, nothing will be able to happen. We would not be able to do work on the universe. The universe will not. So it will just be stagnant, basically. Nothing would be able to happen. And like all the energy would just be, random motions of atoms and molecules in the universe.
I think the way to think about this is that if we think about the two system example where one system is hotter than the other system. At the end, right, when we reach thermodynamic equilibrium, then the temperature of the hot object has decreased, but the entropy has also increased. Now just imagine that like all these hot and cold systems are different parts of the universe. Mm-hmm. And so in total the temperature is going to decrease, like of the hot objects the temperature will decrease, but the entropy will still increase. And so imagine like a star. The system is like a star and like some type of like cold gas cloud, and then once that total temperature or like equilibrates, and then that system comes into contact with something that's even hotter, and then that will just kind of level out everything. Mm-hmm. But the more matter you have, the less the lower the temperature is gonna go to.
Mm-hmm. Also, again, because of the vast size of the universe that we have right now, mm-hmm. right? Because that's what's going to be...
Which nobody actually comprehends.
Yeah, I mean...
You just say the universe is very large. But
because whenever someone says, oh, the universe is 96 billion light years in radius or whatever, like...
No one knows what that looks like.
What does that even mean? Like, how is anyone supposed to ever understand what 96 billion light years means?
Like somebody can understand scales and things. Like,
yeah, that's why you see all those YouTube videos, like scales of the universe, which are actually pretty interesting.
Like you can draw it out and animate it and all that, but your brain will never actually understand what it's like. Mm-hmm. You know, like you look out into the dark sky, and you say that is very far. Whatever I'm looking at is very far away from me, but. You really don't know how far it is.
Because we are what, like 1-2 meter objects, man? Like
we're so used to like
exactly.
We think like far is like across the earth, you know?
Yeah.
we think that's far. We don't know what far is actually.
Like astrophysically speaking, the moment we bring like the universe into the into the picture, like all measurements, even speeds, like. You hear of like planets going in like 11 and 12 kilometers per second. Like, how do you even think about that? Like, that is so immensely fast. Like, kilometers per second.
Relative like, to the sun.
Obviously, relative to different objects, but like, I'm just saying.
If you think about it this way, like the Earth is going, like 11 kilometers per second relative to the sun. The sun is going 200 kilometers per second relative to the center of the galaxy, and our galaxy is going who knows how fast relative to whatever.
Dude, yeah, I mean it's all relativity, right? Like it's all relativity. Yo, we might have to make another relativity episode.
Oh, that's actually true.
I'm telling you, man. I mean, relativity is like a core understanding of any measurement. Any measurement you do, it has to be relative to something else, right? So
that is very true.
Yeah, like it's all dependent.
Unless it's length or mass.
Well.
Oh, actually.
Yeah, length is not one of them.
I just got burned.
Yeah. Special relativity length contraction.
Yeah, very true.
Is the
very
thing.
True.
Yes. So we can't really do that.
So I think this actually concludes our discussion on entropy and the second law of thermodynamics.
Did we touch on the third law?
No.
Wait, did we talk about the third law? And there's no way
I think we might have to save the third law for a thermodynamics part 2 episode. Yeah. If you enjoyed.
Okay.
If you enjoyed this, I mean, do you want to talk about it?
It's not. I mean, like I don't want to postpone it to another episode because it's like a quick law that we're not.
No,
really
we have to leave some suspense. We have to be some good clickbait content creators here.
Clickbait content.
If you want to learn more about thermodynamics, make sure to stick around for the next time we make a thermodynamics episode, which will probably be in like a year from now.
It's gonna be quite a long time from now because we have. I don't know, like we have some really cool episodes coming up. By the way, you guys, like it's some really cool people coming on the podcast. I mean, I'm not gonna spoil anything.
If people actually comment or like message us and tell us to make an episode, we'll actually make it faster than what we planned on doing. Like for example, if you guys comment or DM us on Instagram at math.physics.podcast and you say, please make Special Relativity Part 2. We will
Part
probably
3.
make it Part 2. We didn't make a Part 1. I mean, we didn't make a Part 2 yet.
Didn't we not?
No, we
There's
didn't.
no way there's not a Special Relativity Part 2.
No, we didn't.
What?
But yeah.
Oh, anyway.
We'll be more inclined to make it that way. So
yeah, for
if
sure.
you
No,
enjoyed,
because see, a lot of the ideas that it's like, I mean, not that we have to fully get into a discussion of how we do it, but like a lot of times when Parker and I are like thinking about a future episode, we're just like, hey, what do we want to talk about? And if one of us has an idea, we just flow with it. So if you guys, give us an idea and tell us, hey, maybe this one's really cool, and a lot of people agree with that, then that is very probable, like, to just change our mind. And we're like, okay, let's just do that instead. So, like, right now, it's not very hard to get a certain episode out of us. All you have to do is, like, ask. And especially, like, if we know the topic, then we can do it. Also, we didn't even mention, this should have been mentioned in the beginning of the podcast, but this episode was actually requested by someone months ago.
Yeah.
Right. Yeah, like 2-3 months ago, someone asked us to do an episode on entropy and thermodynamics or something like that.
Mm-hmm.
And we're like, well, we'll do it when we know enough about it.
Mm-hmm.
Right. And we just continued in class. Like we did our own research. Like I think we were pretty confident. And here we are with the episode. So
shout out to that person.
Yeah, shout out. So you might ask us to do something. It might take us time, but we will get it done.
If you enjoyed this episode, make sure to follow us on Spotify or Apple or anywhere you're listening to this.
Mm-hmm.
Anything else, subscribe to the YouTube, go like our videos, make sure to leave a comment, and stick around for next week's episode because it will be a very good one.
Oh.
So this has officially been episode number 52.
Why would it unofficially be episode 52?
Because maybe someone's copying our
anyway,
ideas here.
Continue with the outro.
But this is number 52. I'm your host, Parker.
And I'm Ray. And we will see you soon.
Bye, guys.